Hi. If you have ever been involved in doing mathematics, you might have realized that it is usually presented as consisting of several branches. But in fact, very little is done to demonstrate the link between those branches. This approach is actually quite misleading because mathematics is interconnected and very often ideas from one field help resolve difficult problems in another field. In this video, I wanted to demonstrate a beautiful link between analysis, namely topology, and number theory. These are the two branches that, at a distance, seem completely unrelated. If you want to understand this example, please make sure that you're familiar with the basics of topology, that you at least know the definition. So I want to show that there is an infinite number of primes using topology. Now, primes are of course integers, so I should define some sort of topology on Z. Define a topology on Z. Let's call it T subscript Z. Now, I want to include an empty set to my topology because I want to satisfy the conditions for it being a topology. And I also include sets that I denote S of A comma B for non-zero A, and every such set contains all integers that are congruent to B modulo A. Quite simple. And of course, I want to allow unions of S, A, and B. Now, this is my definition, but I of course need to check that this definition does indeed give us a topology. So the empty set is included, but we also need to make sure that the whole space belongs to our family. Well, if you are aware of what this notation means, if you know basic number theory, this is actually very easy to show. So I will leave it to you as a small exercise. A slightly more tricky bit comes from proving that intersections of these sets are also open. Let's do it like that. Suppose that a certain integer, given integer, belongs to this intersection. Well, using my definition, I can rewrite n as a alpha 1 plus b. So we can rewrite n as this once we're given a and b. And we can also write n as this for some alpha 1, alpha 2 in integers. Now, nothing forbids us from dividing n by a times a prime, right? We just divide it and see whether there is any whole part of a and a prime inside, and we just take out the remainder. So we can also write n as as A prime alpha 3 plus C. So this actually shows us that n belongs to an open set of this form. Now, the only thing left to show is that this open set is actually contained fully inside our intersection. So remember, we are considering this intersection for fixed AB and fixed A prime B prime. So if you have a number x inside this set, again by definition of this set, x is equal to A prime alpha x for some integer alpha x plus C. Now, here's what I suggest. In this part of our considerations, we have studied a specific n. So we know these expansions for a specific number n. We know what alpha 3, alpha 2, and alpha 1 are. So for our general number x inside this set, let us try and express x in terms of n. Now, how would I do it? Well, alpha x is actually alpha x plus alpha 3 minus alpha 3, right? I'm adding and subtracting the same number, but what does it do to our expansion? If we rewrite x with this new substitution, I can then expand this bracket, leaving alpha 3 inside and two other terms outside to get A prime alpha 3 plus C plus A prime alpha x minus alpha 3. Now, this looks a bit obscure, but what we notice is that we have managed to yield n out of x, and the remaining part is divisible by both a and a prime. So what does it mean? Since we know that this specific n is this or this, so we know that x is actually a alpha 1 plus b plus, let's call this r, but it is also equal to, like this expansion, a prime alpha 2 plus beta prime plus the same r, right? But now, as I've noted previously, r is divisible by a and r is divisible by a prime. So actually, we can absorb r into this term with a new alpha. So, if you're not convinced, try to do this yourself. I have just demonstrated that ax belongs to this set as well as to this set. But that's exactly what I wanted to do here when I wanted to demonstrate that this set belongs to this intersection. Therefore, we are done. If you are aware of a more elegant and rather shorter version of this proof, then do let me know. Now, of course, what remains is to show that unions of these sets are open But that is quite easy, because if you have any union of such sets and you pick an element inside, then it will be contained in some specific set which we declare to be open, and that is contained in the union. So union's axiom for topology holds almost by definition. Right, so let us proceed to the actual proof concerning primes. I will make several remarks about our topology, and together they will imply the result. The first remark is actually that S of AB for any A and B is also closed in our topology. Now, if you want to see it, you can just remember that when you divide by A, that is an integer, non-zero integer, there are only A possible distinct remainders, right? So this is a hint, and if you want to show that S of E is B closed, you want to use this fact. The second important remark that I want to make is to say that S of AB is an infinite set. And this should also be quite easy, because if I have a number that is congruent to B modulo A, then I can just add any multiple of A to n, say A times alpha, and that will also be congruent to B modulo A. And of course there is an infinite set from which I can choose this alpha. Right, so how do we get on to primes? Well, let's consider this set for P being a prime number. Again, by definition, this is a set of all integers that are congruent to 0 modulo P. Well, this is the same as all integers that are divisible by P, right? So what happens if I take the union of these sets across all primes? Now, of course, every integer is divisible by some prime number, right? Well, not quite. Remember that 1 is not a prime number. So if we have numbers 1 and -1, this set will not be contained in this union, because P is at least 2 and 1 is not divisible by 2. But of course, the rest of integers will be contained in this union, because there will be at least 2, and so will be divisible by some prime. So if I take integers and exclude this set, I will get exactly this union. Right? So now let's combine our remarks. This set is clearly finite, so it can't be of this form. So this set is not open. We did not define it to be open. But as we know, by definition, closed sets are the ones whose complement is open. So the complement of this set is Z excluding this set. Therefore, this set can't be closed. Not closed. Once again, because this set is not open. But what do we have on the right-hand side? By the first remark, every set in this union is closed. And as you can show by the properties of the topology, if this union is finite, then it must also be closed, because it is a union of closed sets. So let me write it down. If our set of primes is finite, the cardinality is finite, then this union is a closed set. But this is a contradiction, because on the left-hand side, we have a set that is definitely not closed. So we get a contradiction. Now, since there are only two options, that the set of primes is either finite or infinite, this contradiction gives us that this cardinality must in fact be infinite. And of course, primes are contained inside naturals, so they form a countable set. But the important bit is that there is an infinite number of primes. And we are done. It's quite beautiful.